Hello everyone. My name is Lucia Saldana Barco, and today I will be presenting Scaling Multi-Instance Support Vector Machine to Breast Cancer Detection on the BreaKHis dataset. I am an undergraduate student, and this work was performed jointly with Hunse, Dr. Ludovic Brand, and advised by Dr. Hua Wang from the Colorado School of Mines. So first, what to expect. I will begin with some motivation for our work by introducing multi-instance learning and histopathological analysis. I will then follow this with some context on the breast cancer histopathological database, also known as the BreaKHis dataset. I will continue with a discussion on the accomplishments and limitations of the various related works done in computer-aided diagnostics, as well as an introduction to our proposed method, a primal dual multi-instance support vector machine. This will be followed by a series of experiments exploring the performance and scalability of our method on the BreaKHis dataset. And finally, I will conclude this presentation with a summary of our contributions. So as I said, I will begin by explaining the motivation for this work. There are two perspectives at play here, the clinical and the machine learning perspective. We will explore each of these separately at first, and we will bring them together throughout the remainder of this presentation. So according to the CDC, every year, approximately 250,000 women in the US are diagnosed with breast cancer. Another way to look at it is that 1 in 8 women will be diagnosed with breast cancer in her lifetime. Now, the good news is that according to the American Cancer Society, breast cancer death rates declined 40% from 1989 to 2016 among women, and the progress is attributed to improvements in early detection. This is what motivates us, the fact that we can, to some degree, contribute to the early detection of breast cancer so that death rates continue to decline in the years to come. So differentiating between the different types of breast cancer is essential for making an accurate diagnosis. Histopathology is the close examination of tissue sections with a microscope to aid in the diagnosis of illnesses such as cancer. These tissue sections can also be called whole slide or histopathological images when they are digitized. Traditionally, clinical disciplines such as radiology and pathology have relied heavily on specialized training to detect the presence of these diseases in histopathological images. Doctors can make a diagnosis based on features exhibited by tissue samples on a cellular level. An anomaly in the cell architecture and the presence or absence of certain biological attributes can be strong indicators of a particular disease. A pathologist can detect this abnormal growth or tumor from a histopathological image and assess which regimen should be prescribed to halt the progression of the disease. Modern medical procedures and technologies have increased the number of biopsies performed, and consequently, the number of histopathological images collected has increased far beyond the reasonable workload of pathologists. However, recent advancements in the field of artificial intelligence have shown promise in automating the analysis of vast amounts of medical data and improving the accuracy and speed of a diagnosis. So as I mentioned in the introduction, there's another perspective that we must consider, which is the machine learning perspective. So let's talk about the difference between single versus multi-instance machine learning. In the single instance learning paradigm, a dataset X contains a series of columns that represent each instance within the dataset. In this learning paradigm, each instance is associated with a label. On the other hand, in the multi-instance learning paradigm, a dataset X is broken up into column blocks Xi, where each column block is known as a bag, and each bag is associated with a single label. Because of this, clinicians don't need to spend a lot of resources into characterizing each image obtained from a biopsy. Doctors only need to label the bag or patient as malignant or benign, and the rest of the instances or histopathological images follow suit. This is the main reason that we believe multiple instance learning would be the better choice for disease detection applications. I will now introduce the source of the data for our experiments, which is the BreaKHis dataset. So the BreaKHis dataset was built in collaboration with the PND laboratory in Paraná, Brazil. The samples were acquired from 82 patients whose data were anonymized, and the samples were collected by surgical open biopsy, also known as SOB. The images were labeled in the P&D laboratory, and the diagnosis of each slide was determined by experienced pathologists. The dataset itself is broken up into two categories, malignant and benign tumors. Each of the groups is further divided into the specific type of tumor within that category. On the screen, you can see each type of tumor along with the number of patients that are diagnosed with it. And each of those patients is represented by their images, which were collected using different magnifying factors. So let's illustrate all this information. A patient has a sample extracted through surgical open biopsy, and this sample is then digitized into a whole slide image. Images are taken from the whole slide image at the magnification levels that you can see on the screen. And these are all the histopathological images that represent a single one of the 82 patients from the BreaKHis dataset. Now, in our work, each of these images is thought of as a multi-instance learning bag, and we select a random number of bags from each patient, and then we randomly choose the number of patches to extract from each bag. So we can extract 1, 5, or 10 patches from each of these bags, like so. Next, we use each of these patches to extract a feature vector through the parameter-free threshold statistics method. PFDAS is a method that extracts texture features by counting the number of black pixels in the neighborhood of a single pixel. And the total count for all the pixels in a given image is stored in a 9-bin histogram. The thresholding is done by Otsu's algorithm, and the extractor returns a 162-dimensional feature vector. We repeat this entire process for each patient, and we concatenate the information extracted from all the patches to get all of our features. I will now talk about the current computer-aided diagnostic methods and their different approaches to histopathological image analysis. So the first type are convolutional neural networks. The deep structure of CNNs can achieve state-of-the-art performance in image recognition tasks. The model AlexNet has been successfully applied to the BreaKHis dataset. However, some of the obstacles that CNNs face is that training requires a large amount of data and great computational power, which makes it difficult for predictive models to be combined with CAD systems. The second type are support vector machines, which have achieved a promising accuracy higher than 90% in image classification. SVM does require less training time and computational cost than CNNs. However, training time and computational complexity increase very rapidly as the number of input features increases. Another problem of traditional SVM models is that they are single instance models, which means they are not able to handle a varying number of input instances. The last method I will cover are multi-instance learning methods. These types of algorithms have also been evaluated on the BreaKHis dataset previously with satisfactory results. However, these existing MIL algorithms do not scale well to larger datasets, which makes it hard to use them in practice. To address these limitations, we present an objective and associated solution of the novel primal dual multi-instance SVM that extends to large-scale data. We also develop and improve the optimization technique based on the multi-block alternating direction method of multipliers to bypass the quadratic programming problem that comes from the typical MISVM models. So to put it into context, here's a visualization of our processing pipeline for our multi-instance learning algorithm applied to the BreaKHis dataset. As I said before, we sample the patches from the bags at 4 different magnification levels and process the patches with the PFDAS method, which results in the feature vectors for each image. Finally, our multi-instance SVM classifies the bags as malignant or benign. So before we begin, here's the notation that we use. Scalars are represented by lowercase letters, vectors by bold lowercase letters, matrices by bold uppercase letters, and given a matrix M, its ith row and jth column are denoted as M superscript I and M subscript J. And a scalar value indexed by the ith row and jth column of matrix M is denoted as M superscript I subscript j. The matrix MP corresponds to the pth column block of M. And then lastly, each bag contains Ni patches, and it is associated with an mth class label. So this is the original MISVM objective that we aim to minimize. Since this objective is generally difficult to solve because of the coupled primal variables WK and BM, as well as the max operations, we split the primal variables by introducing some constraints, and we derive the following augmented Lagrangian, which you can see on the screen. So here we converted the original constrained MISVM into this new unconstrained objective that we intend to minimize. In this section, we derived the efficient solution algorithm to minimize the objective in the previous slide. We discard all the terms that do not include W, and we optimize the columns of W separately by solving these K problems for M1 through K. Here, N prime is the number of bags which belong to the nth class, and I prime denotes the indices of column blocks of X. Next, if we let the derivative of this equation, equation 5, with respect to Wm equals 0, we attain this closed form solution, which is the efficient update of W for MISVM without a kernel. Now, in the calculation of this equation, we can avoid the inverse calculation through a least squares solver. However, the least squares solvers are pretty slow, so we aim to avoid this, and I will explain how we avoid it in a couple of slides. The kernel method is widely used in classification tasks to deal with nonlinearity. Here we provide the kernel extension of our method to learn the nonlinear relationship between bag and target label. Notice that in this equation, we avoid to compute the feature vectors phi in the possibly large dimensionality dz. So we compute the inner product of feature vectors phi hat transposed and phi hat, instead of directly computing the product of vectors phi and phi transposed. You can find the full algorithm and derivations, as well as a more in-depth explanation in our paper. As I promised before, I will now talk about how we avoid that least squares calculation. So here in equation 6, the inverse matrix calculation requires a least squares solver in every iteration. However, the least squares solver has complexity OND squared and will have to be solved every iteration, which may not be computationally feasible if the number of features D is very large. So we avoid the least squares calculation with the optimal line search method, which updates Wm via gradient descent. Delta Wm is the direction of the update, and Sm star is the amount of the update for W. So essentially, we optimize direction and amount of update. Now, if we get equation 24, which is the minimization from the previous slide, and we differentiate with respect to Sm, and we set that result equal to 0, we get equation 25, which you can see on the screen right now. And this will be useful because if we plug in equation 23 and equation 25 into equation 22 to get an efficient update equation, which avoids the least squares problem in equation 6, the time complexity of the proposed method is ONDN bar, where n bar is the average number of instances per bag. The number of instances n bar is typically smaller than the number of features D, which is a multiple of 162 in our experiments. Therefore, our inexact PDMISVM with the solution in equation 22 is more scalable compared to the exact PDMISVM. In our experiments, we evaluate the classification performance and scalability of the proposed exact and inexact PDMISVM implementations. The scalability of PDMISVM is assessed across the increasing number of bags and features, and we also identify the disease-relevant patches of each bag. So we compare our method against popularly used algorithms. The single instance learning method assigns the bags labels to all instances during training. We also compare it to the normalized set kernel and statistics kernel, which are two bag-based methods that map entire bags to single instances using a kernel function. Another one of the methods is the axis parallel rectangles algorithm, which is an MIL model which starts from a single positive instance and grows the APR by expanding it to cover the remaining positive instances. Furthermore, we compare our method to MINet and capital MINet, which are two end-to-end deep neural network architectures which have been used for multi-instance learning. We also compare it to AMIL, which calculates the parameterized attention score for each instance to generate the probability distribution of bag labels. And we also compare it to LAMIL, which learns the instance scores and predictions jointly by integrating an attention mechanism with the loss function. Ours is the derived primal dual multi-instance SVM method, and ours inexact is the inexact variation using the optimal line search method to improve scalability. Here is the classification performance of our PDMI-SVM and competing models with the different magnification levels. The precision, recall, F1 score, accuracy, and balanced accuracy are calculated across 10 six-fold cross-validation experiments. The best scores are highlighted in yellow. And from the results reported here, the proposed exact or inexact PDMI-SVM show promising performance across the various magnification levels. In particular, as you can see, our exact PDMI-SVM outperforms the other models based on recall. And our high recall rate is critical in the medical domain, as false negatives may result in serious consequences. These results show the clinical utility of our model, as it is crucial not to miss a malignant tumor in the diagnosis. Finally, let's end with the contributions of our work. So the main contribution of this study is that the derived algorithm scales to the large data set. We plot the training time of the classifiers on the BreaKHis dataset to verify this improved scalability against the number of bags in Figure 3 and the number of features in Figure 4. In Figure 3, you can see that our PDMI-SVM outperforms the other models in training a large number of bags, which validates the superior scalability of the proposed primal dual approach over the other SVM models, which rely on repeatedly solving a quadratic programming problem. In Figure 4, we compare the training time of the exact and inexact versions of our models to the other competing models. Ours inexact and APR spend the smallest training time when trained with a large number of features. Interestingly, the inexact variation of PDMI-SVM scales significantly better than the exact PDMI-SVM against the increasing number of features, where the number of bags is fixed. This is well represented by the analytical complexity of the two derivations. Along with the improved prediction performance and scalability, our model, PDMI-SVM, can identify disease-relevant locations. The interpretability is crucial as it can add confidence to the generated predictions and help clinicians use histopathological references to make a diagnosis. The patches identified by our model are in accordance with the clinical insights. For example, from the identified patches on the top row, our model can reveal that the nuclear to cell volume ratio is consistent throughout, and there is a continuous organized distribution of cells, which are distinctive features of non-carcinomas. Because of this, our model correctly classifies the bags as benign. And from the 3 malignant samples in the bottom row, you can see that our model correctly classifies the bag as malignant.
Can you quickly conclude, please?
Yes. So we present the primal dual multi-instance SVM, as well as an efficient optimization, which is scalable to large data sets and computationally efficient, and has promising prediction performance. And then, thank you very much for listening. This work was done by Hunse, Dr. Ludovic Brand, myself, and Dr. Ho Wang. If you have any additional questions, please feel free to contact us at these emails. And thank you very much.